Okay, so part two of the week 3 lecture intro to reading is about energy and radiation. So we're going to look at some concepts of heat transfer, general topics around insulation, the energy balance, and albedo. So just remember in the previous video we talked about the electromagnetic spectrum, and so when we talk about radiation, we're talking about incoming solar energy or radiant energy coming from this visible light and ultraviolet light, and having that hit the Earth's surface and be converted to long wave radiation. Now, it's important that you understand ways that heat can be transferred. So we're not talking about energy coming in, we're talking about once the surface of the planet has warmed up, what happens to that. And so there's three methods of heat transfer that I want you to be able to talk about. The first two are conduction and convection, and people typically use a stove to show this. So conduction is that energy that's transferred from direct contact. So if you took your hand and put it on a hot burner, the bottom of your hand, or the part that you touch to the burner, is going to get hot immediately. It's going to have that molecule transfer, and if you leave it there long enough, the rest of your hand will get hot. So you can think about putting a pan on the stove and the bottom of the pan gets hot. It takes a while for the handle of that pan to get hot. Convection is the energy that happens through some kind of motion or circulation. And so if you had a pan of hot water on the stove, conduction is going to work first, and the conduction is going to heat the bottom of the pan, and then the bottom of the pan will heat the water that is at the bottom of the pan first, and then as that water gets hot, it becomes lighter and moves to the top of the pan, and as it moves to the top of the pan, the colder water or liquid flows down to the bottom of the pan, and that creates a circulation. And you can see that circulation in many factors. So we'll see circulation or convection circulation as an important factor of earthquakes and volcanoes. The whole magma moves in circulation from hotter interior core floating up to the surface in cooler, heavier magma or a rock being pulled down to the core. You also see that in oceans where cold water sinks to the bottom of the ocean. Warm water tends to rise, creating circulation, and we'll see that in wind patterns where hot air will rise and cool air will sink down. So this idea of convection, once the surface gets heated through conduction, is critical to the planet. The third type of energy transfer is called advection. And advection is the horizontal transport of energy. And so once energy starts to move up, whether it be magma or water or air, if we're talking about air, it's that transportation or sideways movement of heat, usually caused by wind, which you're not going to see in the magma or in water. Okay, the book talks about the solar constant, which is kind of the global average amount of solar radiation at the top of the atmosphere. But when you get to the surface, the solar constant is really variable. And this is due to the angle of the sun. Remember, if you have direct subsolar point at the surface, that's going to have more sunlight than further up in the column of air. It's also going to be changed by a very steep sloping ground. It's not going to have direct insolation, or if you have clouds and other atmospheric particle, that will block the solar constant. So again, that angle of the sun can increase the amount of wattage per square meter if it's direct or if it's diffuse. And the diffuse solar energy can also happen if you have it hitting on the angle of a mountain. So just make sure you kind of understand that geometry. And so when we're talking about the solar constant and the variability in that solar constant, again, if you have a lot of dust particles or atmospheric particles, that's going to block or reflect some of that solar insolation. So again, beautiful sunsets, but maybe not as warm, not as much sun getting to the surface. And again, a cloudy day is going to block off some of that solar energy. So when we look at the Earth's energy budget, I've seen this called, let's see, there's a bunch of different terms for it: radiation budget, energy budget. And I think there's a different image in the reading. It was too big to put in the PowerPoint. But this gives you kind of that general idea of the different things that can happen to that solar insolation as it's coming in. You have 100% of solar insolation coming into the atmosphere. About 6% gets reflected by the atmosphere as it goes through those different layers. About 20% gets reflected by clouds. Some places have more clouds than others. The Earth's surface reflects another amount, about 4%. And then there's some sideways transfer. And then when you get to the surface, so you get about 51% of the incoming solar radiation gets to the surface to warm up the ground, and then that gets turned into what's called long wave radiation, or heat energy, or heat waves, and that begins to rise because hot air rises, correct? And again, that can go out into the atmosphere, or it can be stopped and reflected back by clouds. So it's just important to kind of have a sense of the different pathways that shortwave radiation can have as it comes into the surface, and what happens to long wave radiation. So here's an image I love of a guy standing here. Obviously you can see in the reflection on the glasses he's on a snowy slope. And so, you know, have you ever been out on a snowy slope on a sunny day and you get a sunburn? And sometimes people get a sunburn on their chin or under their nose because the sun coming in will reflect off that very bright snow surface and actually cause sun blindness. You've heard about that, or just people getting sunburn. So that's the aspect of what's called the Earth's albedo. The Earth in general has an albedo of about 31%, but based on the different surfaces, different aspects of the Earth have a different albedo. So fresh snow, about 80 to 95% of shortwave radiation will reflect off the Earth's surface without being absorbed. And if you see this example of asphalt or blacktop, only about 5% of the solar insolation gets reflected off. That means 95 or 90% actually gets converted into long wave heat radiation. So it's really important when you look at the Earth's ability to heat and cool itself that you understand the albedo, or the reflectivity. And if we dramatically change the albedo of the Earth's surface, we're going to have consequences. So here's a couple examples. This is an example of some glacier melt. You can see in 1938, black and white photo, but you could see all of the gray, stripy, dirty, white area was glacier. In 1981, you see the glacier has retreated and there's a glacial lake. 1998, less glacier, lots more lake. In 2005, much less glacier. And this really shows you a great example of positive feedback loop, where the less reflectivity of snow that's available, then the more absorption by rock and other elements that will heat the ground, causing more snow melt, that will heat the ground, causing more snow melt. Another thing that you can see as a result of albedo is what are called urban heat islands. So when you look at late afternoon temperatures over a city, you'll notice that if you go out into the rural areas or the suburbs, in the afternoon the temperature is considerably less because there's less asphalt, less buildings that will absorb the heat. There's more reflectivity in forests and farms, and so you get these really intense heat islands caused by human altering of the surface. So overall, when you look at incoming solar radiation, and remember we're thinking about the image of how sun moves latitudinally, so at 25.3 north and south is the extent of the subsolar point on the Earth, and so we have a surplus of heat here between 23.5 north and 23.5 south. Actually, it goes a little beyond that, and then there's a deficit or not enough shortwave energy in the polar regions. So if this were the actual representation of Earth's planet, we would not be able to live where we live. What you actually see when you look at the net radiation is that you see it is not completely linear. Yeah, there is a lot more heat along the tropics, a lot cooler in general on either side, but because of ocean currents, because of conduction and convection and advection, they work together to take that excess surplus heat away from the equator and move it poleward. So without that heat transfer, the equator would be much too hot and the mid-latitudes where most of us live would be much too cold. So because of air and water circulation, it means that at this point the planet is just right.